All right, good morning, ladies and gentlemen, friends and neighbors. We're going to start a discussion about parametrically defined functions. And we could call these problems bug movement in the XY plane. Keep in mind, we have looked at bug movement in the XY plane, but we have looked at movement on the x-axis independent of bug crawling on the y-axis. Here we're going to combine the two um, concepts, if you will. So parametrically defined functions simply give us another way to describe points in XY land. Instead of defining y values as a function x, or even defining x values as functions of y, which we've done before, using the very common notation y is equal to f of x or x is equal to f of y, we define both the xy coordinates as a new function of t, x of t, y of t. And you'll get that here in a little bit. It is important to note that we indeed are still in XY land. We absolutely still in XY land. 99% of what we do will be in XY land. Okay, so here's a simple example to start off with. On the grid provided, plot the points that are defined parametrically, where x is equal to 2t plus 3, y is equal to 4t minus 3, and we're going to make a table of values. So I just want t is going to range from 0 to 3. So I'm just going to write, I'm going to have a little chart here. I'm going to go t values, x values, y values, and my t's will range from, and I'm going to use integer values of t. You don't have to, but it's going to make for best discussion. So I'm going to 0, 1, 2, and 3. And what I want to do now is I'm going to find the x and y point for each of these time values here. Okay, you can do this with your calculator or however you want to do this, but I have the points defined already. So let's see here. So when t is equal to 0, the x is going to be -3, or positive 3, sorry. Going to be 3, and then the y is going to be -3. That's an easy one. We didn't need the calculator to do that. We really didn't need the calculator to do any of these, but just to verify. And then if t is equal to 1, what do you have? X is equal to 5, and y is equal to 1. And if t is equal to 2, I have y is equal to 7. Or, pardon me, x is equal to 7, and y is equal to 5. And for the last t value, I have t equals 3. If t equals 3, then the x will be 9, and the y value will be 9 as well. So what we're going to do is we're going to plot these points, but we're going to have to, you'll see, we're going to put a directional arrow on this graph, because we're only talking about 0, where t is between 0 and 3 exclusive. So if t equals 0, it looks like we're at the point 3, 3. And so we're going to go to 9. So I'm going to go in increments of 2 here. Whoopsie. 2, 4, 6, 8, 10. So I get this 9 in here. 2, 4, 6, 8, 10 over here. And so if t is 0, you don't plot these points here. This t was just to get these points here, 3, -3. So let's go 3, -3 first. I got 3, -3 is going to be right there. That's when t is equal to 0. Then when t is equal to 1, I have 5, 1. So I have 2, 4, 5, 1 is going to be about right there. And when t is equal to 2, I have 7, 5, 2, 4, 6, 7, 2, about right in there. And then the last point of t is equal to 3, I'm going to go to 9 to 9. Well, 9 to 9 is about right in here. And what I'm going to do here is I started at this point, so I'm going to sketch my graph, and I'm going to put arrows on it, because that's the way that was the direction that parametric curve went. Because t0, I went from -3 to -3 all the way up to 9 to 9. So it is that simple, ladies and gentlemen, graphing parametrically defined equations, if you will. And let's do another example here. Okay. Okay, so now, and I know most of the application problems in calculus, the t's will always be positive, but just for educational purposes and for understanding purposes, we're going to let t range from -2 to 3. So when I do my chart here, I'm going to go -2, -1, 0, 1, 2, and 3. And so this will be my t values. Then I have a column of x values and a column of y values. Okay, and let's see what those guys are going to be, and I'll let you, you can figure those out if you're on your own if you like. I'm going to grab my graphing calculator real quick and put those babies in there. So t squared plus 2t, and I have t squared minus 5t. Okay, let's make sure I haven't, and I will show you when I get back how to easily put these in your calculator. There's a parametric mode that you can put in. T squared plus 2t, t squared minus 5t, yep. And now I'm going to start at -2 this time. -2, bam, -1, bam, 0, bam, 1, 2, and 3. And let's see what points we get. So when t is -2, looks like I have the point 0, 14. When t is equal to -1, I have the point -1, 6. I'm just putting these t values into these x and y functions. And when t is equal to 0, I'm going to have 0, 0. It's an easy one to plot. T is equal to 1, I have 3, -4. T is equal to 2, I have 8, -6. And you can always pause the video and verify that my numbers are correct. I believe they are. And then if t is equal to 3, it looks like I have 15 and -6 again. So we're going to plot these points. Looks like we're going up to 14, or the y's are going to go to 14. I bet we can go 2s, 2, 4, 6, 8, 10, 12, 14. Yes, we can. So we're going to go 2s all the way around. 2, 4, 6, 8, 10, 12. Doesn't matter. I don't think we're not going to. Yeah, we're going to go up to 15. 2, 4, 6, 8, 10, 12, 14, 16. All right, so let's plot our points. And we're going to be very careful to add a directional arrow once we get the graph completed. Okay, so we're going to, first thing, we're going to start at 0, 14. So I'm going to go 0 all the way up here to 14. That's this point right here. Then I'm going to go -1, 6. -1 here. 6 is going to be right there. -1, 6. I'm going to go back to 0 at 0. I have the x, y, 0, 0. And when t is equal to 1, you have the point 3, 4, 2, 3, all the way up here to 4, or -4, 3, -4. So we're going to go down here. And then when I'm at 8, 2, 4, 6, 8, I'm at -6, which is down here. And when I'm at 15, I'm at -6. So 2, 4, 6, 8, 10, 12, 14, 15 right here, I'm at -6 as well. And so now I'm going to sketch my graph. Keep in mind, I could go more t values between -2 and 3, but this is going to give us a good idea. So here comes the sketch of my parametrically defined curve, if you will. This was the initial point, and we're going to put arrows signifying this is the direction that we're going. Okay, pretty easy to plot these things. Now, here's a good question. I am in x, y land. This graph is neither a function of x or a function of y. It's a parametrically defined function, which is infinitely many points between the starting point and ending point. Is there a spot on this graph where the points are farthest to the left? Oh, yeah, there is. And that point would be about right in here, somewhere about right in here. That point is going to be the point farthest to the left. Is there a point on this curve that is farthest going down? There is right here. It's that point right there. And here's the key about these parametrically defined functions. We are in XY land, and we've done this with implicit differentiation. If we're in XY land, there's no reason at all why we can't talk about this guy right here, dy dx. What is dy dx? Well, the slope of a tangent line. And eventually, I'm going to show you how to find dy dx given these two parametrically defined x and y's. But what would dy dx be, just for giggles? What would dy dx be at this point right here? Wouldn't dy dx at that point right here, the dy dx would be undefined there. And another interesting point would be here, where the dy dx would be equal to 0. And so don't forget what we already know about dy dx. Dy dx is the slope of a tangent line, and as long as we're in xy land, which we are, we're going to be able to find dy dx. So let's go to the next page. The next page has some very important definitions, and then eventually we're going to just look at some examples using these definitions. So let's jump to the next page, if you will, please. And here we go. Well, golly, if you look at this first statement here, we determine if a bug is moving to the right or to the left with the sign of dx dt. Well, we knew this before. We could talk about dx dt, and if it's positive, the bug is moving to the right. If it's negative, the bug is moving to the left. So don't forget what you already know. We're just combining some things together. Bullet number 2 here. We determine if a bug is moving up or down with the sign of dy dt. If dy dt is positive, the bug is crawling up. If that is negative, he's crawling down. What we're going to do is we're going to combine this, because a bug, no bug crawls in an exactly horizontal manner or exactly vertical manner. And if I go back to the next slide, if I just look at this example here, this first example wasn't. If I look at this guy right here, and this is the bug, we'll let the bug be purple. Here's my bug, and he's starting to crawl. He's starting to crawl. This is slow motion. He certainly is crawling down, and he's crawling to the left. So I would think that when this bug starts crawling, the dx dt, whatever that is going to be less than 0, because he's crawling to the left, and the dy dt is going to be less than 0 because he's going down. So he's going to the left and down. So that would signify that both of these derivatives, dx dt and dy dt, both are negative. So that's going to be a very useful definition that we've talked about before, these guys here. We determine the rate of movement of the bug up or down with the second derivative of x with respect to t and the second derivative of y with respect to t. We don't use this very much, but it was worth actually mentioning in these notes. The next thing we're going to talk about, we're going to double star this, maybe even triple star this, is the slope of the path of the bug, or the slope of the tangent line to the graph of that bug. And we've been talking about tangent lines a lot. And what is that tangent line? What is the slope of that tangent line? Is dy dx. And we know that. The slope of any tangent line in xy land, if you're talking about polar, parametric, implicitly defined functions, the dy dx is always the slope of the tangent line. Well, if I look at this equation right here, dy dx is equal to dy dt over dx dt, it's easy to see that the dt's will cancel. You can get those out of here, and dy dx is equal to dy dx. So this is easy to remember, and it's going to be easy to find dy dx for a parametrically defined function, because we're going to have to find the dy dx many times. We will also be asked to find the second derivative of y with respect to x. And I'm going to tell you, this is hard to do and hard to remember. If you think about the box method, It makes it a little bit easier. We may or may not go over one of these examples because they're not too awful important, but important enough to certainly add it to our curriculum here. So this, what is this? What is that? That means this. This guy here means I'm going to take the derivative with respect to x of the derivative with respect to x. That's what this notation means. And so I'm going to use, if I look at this equation here, instead of y, I'm just going to use box. The derivative of box with respect to x is the derivative of box with respect to t divided by the derivative of x with respect to t. This is the same formula as above, but only what are we doing? We're putting this box in for dy dx. So let's get wild and let's do an example of finding the dx dt, the dy dt, and the dy dx. So let's, here's a parametrically defined motion right here. I'm going to let x of t equal 4 sine of t. And I'm going to let y of t equal 4 cosine t. And my objective is to find x prime, dx dt, dy dt, and dy dx. So what is dx dt? I mean, we could call it, if we want just x prime. X prime is going to be easy. It's going to be 4 times the derivative of sine. The derivative of sine is cosine. So that's x prime. We could call that dx dt if we want. And we know that, certainly. Make sure the x looks like an x. And in like manner, we're going to find y prime. And y prime is going to be pretty cut and dry. It's going to be 4 times sine of t. Oh, but wait. Derivative cosine is negative sine. So there's my dx dt and my dy dt. And now look how easy it is to find the dy dx. The dy dx is simply equal to the dy dt, which is this guy right here, divided by the dx dt. Well, what is the dy dt? Negative 4 sine of t. And dx dt is 4 cosine of t. And I will tell you, you could write this like this if you so desire. The 4's will cancel. Or you certainly could just write it as negative tangent of t, if you will. Okay, I'm going to hold off finding that second derivative because it's cumbersome. And we're going to go light in this video. All right. So let's see what else is on the docket here for this particular video. What's the next page talk about? The next page is very important. And we have not done this yet. It will be very useful to find the length or the distance that a bug has crawled on a curve over a certain amount of time. If we were going to go back to that very first example, here's what we're going to do. What I'm actually going to do is to find this distance. I'm going to find that distance that bug crawled. That's the distance that bug crawled. Or you could also call that, that's an arc, the length of the arc. You can call it either thing. But for right now, we're going to just call it the length of that curve. And here's the formula for that if you want to find the length of the curve. Okay, the length of the bug, the length L, a bug crawls on a curve from t equals a to t equals b is given by this formula right here. We're going to integrate from a to b the square root of the first derivative of dx dt squared and dy dt squared. I could show you this proof. It's very easy. It's based on the Pythagorean theorem, but since we're a little bit, strapped for time a little bit, we're just going to know how to use that and apply that. And I'm going to go back to that very first example, or the second example, sorry, and I'm going to find the length of that curve. Okay? Oh, let's see what that particular example was. That particular example was this guy right here. I have x of t is equal to t squared plus 2t, and y of t is equal to t squared minus 5t. And what I want to do is find the length of that curve. Well, I'm going to need to find the derivative, dx dt. Dx dt is 2t plus 2. And y prime of t is going to be 2t minus 5. So there's my derivatives. And keep in mind, for that particular problem, the t values went from -2 to 3. So here's the length of that curve, or the total distance that that bug crawled. We're going to call it the length. Is going to be the definite interval from -2 to 3, the square root of x prime squared, so it's going to be 2t plus 2 squared, plus dy dt, which is 2t minus 5 squared dt. And I'm going to tell you, ladies and gentlemen, you would never, this is a calculator active problem. We definitely will not use the analytical method to do that. I don't even think you can. So I'm going to calculate that for you here momentarily and get us an answer. So I put that into my graphing calculator, and I did the integration, and the length of that curve is equal to 31.723 units. And I would challenge you to put that in your calculator and make sure you get get that answer. That is correct. I double checked my work. And if I go back to my original, that seems like a big number, but if I go back to my original slide that had that curve on it, right here, what, about 32? Well, check this out. I have 2, 4, 6, 8, 10, 12, 14. That's about 14 stretched, so it's a little bit more. And I have 2, 4, 6, 8, 10, 12, 14. 14 stretched a little bit more. So that number of 32 does make sense, that number 31.723. So that certainly does make sense. So what I'm going to do is I'm going to pause the video here. I will have some problems assigned where you find the length of the curve and find out when dx dt is 0 and dy dt is 0 and all those things. This will be a very good video to get you started, and I will see you soon.